Welcome in! Our objective for this video is to learn how to rewrite reactions as complete molecular reactions, ionic reactions, or net ionic reactions. Many of the reactions and chemistry that we see in this course will be in water, dissolved in water. We call things that dissolve in water aqueous. These are homogeneous mixtures with water as our solvent, water as our main component. A difference between ionic and molecular compounds is that ionic compounds dissociate into their component ions when they dissolve into water. As a solid, NaCl has this repeating crystal structure of sodium ions and chlorine ions. But when it dissolves, those ions are broken apart and we are left with those individual ions floating around, separated from each other. Note here, this is the ions that are separated. If you have polyatomic ions, those polyatomic ions are still grouped together, moving around, bonded together as a group. They're just separated from what other ion they had been attached to. Here's what this looks like. If you have sodium chloride in water, aqueous, our sodiums and our chlorines are totally separated from each other. All we have are those individual sodiums and those individual chlorides floating around doing their own thing. There is no more sodium chloride there together. All of it has turned into those little individual ions. Likewise, if you have polyatomic ions, like silver nitrate, this dissolves to produce our silver ions and our nitrate ions. That nitrate still exists as that polyatomic group, but it's been completely separated from the other ion, which is silver, in our solution. We can introduce some terminology. Soluble compounds are ones that dissolve in a liquid. For ionic compounds, this means they exist as those individual ions, those individual pieces. Not everything dissolves. We can call things that do not dissolve insoluble. We're going to introduce a set of rules to decide whether we expect something to be soluble or insoluble. This is a good set of, rule of thumbs to describe whether something will dissolve or not, at least based on whatever ions are present. Here is our chart, and I'll let you have access to this handout while taking quizzes and exams. So no need to spend a ton of time memorizing, but we do want to be able to know how to read this chart. The top of our chart are things that are soluble. Anything that has these group 1 ions is going to be soluble, is going to dissolve. We can write the phase as AQ, aqueous. However, our rules oftentimes have exceptions, so we can check soluble except, in this case, no exceptions. But if we have something like our halogens, these are soluble except when they pair with silver, mercury, or lead, then it will be insoluble. In other words, we can say that they will remain solid. The bottom of the chart is organized in the opposite way. These are compounds that are mostly insoluble. They will remain as a solid most of the time. Things that contain hydroxide or sulfide will likely be solid. Once again, we have some exceptions though. When these pair with those group 1 ions from up above or some other exceptions down here, then they will be soluble, AQ. This is how we like to read this chart. The top left are things that are soluble, aqueous, but double check on the right that we don't have one of those exceptions. If we have something at the bottom left, these are insoluble or solid, but double check that we don't have something on the bottom right, then it would be aqueous. If we want to check a couple of chemicals, if we have silver bromide, we don't have any rules on the left-hand side for silver, but we do have a rule for bromide. Bromide compounds tend to be soluble. However, we can check, is this one of our exceptions? And the answer is yes, this is an exception. So we can say that silver bromide, even when it gets dumped into water, will remain as a solid. A second example, we can look at iron 2 sulfate. We don't have a rule for iron, but we do have a rule for sulfate. This tends to be soluble. We can check though, do we have one of our exceptions? In this case, no. So we're going to stick with our regular rule, which is sulfate compounds like to dissolve. One more example, if we have something like copper 2 sulfide, we don't have a rule for copper, but we do have a rule for sulfides. These like to be solid, except when our sulfur pairs with one of these things, or any of these ions from the top left. We don't have one of those here. We have copper 2 instead. So this has to be just our regular rule. This is going to be solid. Another quick example here. If we have barium chloride, pause the video, go back to the solubility rules, and decide what phase you expect for BaCl2. We should decide that this is aqueous, dissolved. When our ionic compound dissolves, it will actually exist as those individual pieces, barium ions and chloride ions. Which of these pictures represents those individual ions totally separate from each other, floating around doing their own thing? Has to be that first one. In our previous video, we looked at a couple of balanced chemical reactions. We had written down what are called molecular equations, molecular reactions, which show all of our compounds as those neutral formulas, even if they're mixed with water. This is not the most accurate representation of what is actually floating around in our beaker, although it is a nice way to represent our molecules as formulas, and if we are good chemists, we do have intuition of what actually is floating around, just like the picture we saw on the previous slide. But if we want to be more explicit, we can rewrite things as what we call ionic equations. The complete ionic equation takes everything that is aqueous and rewrites it as the actual ions that exist floating around in our beaker. Silver nitrate, we saw a few slides ago on the picture, actually exists as silver ions and nitrate ions. Sodium chloride we saw as well. This actually exists as sodium ions and chloride ions. Our complete ionic equation, we want to actually write this out as those individual pieces to give some better intuition. On the product side, we have sodium nitrate as aqueous, Let's write that as those individual pieces. If you have anything that is a solid or a liquid or a gas, we can leave those exactly as they are. This is rewritten, just copied over, AgCl solid. Notably here, we have a few ions that are highlighted and labeled as spectator ions. Spectator ions are present in the beaker, but they're exactly the same before and after the reaction. They're floating around by themselves and they're unchanged. They aren't actually participating, they're just floating around and watching, like spectators. If we want to do less writing, we can do our net ionic equation and rewrite that complete ionic equation without the spectator ions. If we subtract a nitrate from both sides, subtract a sodium from both sides, we're left with a much simpler representation of what's in our beaker, while still giving that intuition about how these ions actually exist, floating around, bumping into each other as those individual pieces that form into a solid. Let's run through an example here. If we have PbNO32, this is aqueous, so let's rewrite it as the individual pieces. When we're doing this, it's important to include the charges. Here we have lead 2, and we have nitrate, which always has a charge of -1. We're reacting with lithium chloride, which again is aqueous, so let's break it up into those individual pieces. On the product side, PbCl2, lead 2 chloride, is a solid. Don't change it, just copy it right down. Lithium nitrate is once again aqueous, so we can break that up into lithium ions and nitrate ions. Don't forget to include your phases for everything. I know it's a lot of writing, but this is part of it. And lastly, since our reaction was balanced to begin with, let's make sure that it stays as balanced. In lead nitrate, lead 2 nitrate, how many leads did we have? Well, just one. How many nitrates did we have? Oh, that subscript will turn into a coefficient. If we have 2 lithium chlorides, how many lithiums do we have? Well, this coefficient is going to affect our amounts as well. We have 2 lithiums and we have 2 chlorides. For lithium nitrate, we have 2 lithiums and 2 nitrates. We can do our tally and double check that this is balanced, but the short of it is coefficients will affect our amounts and subscripts will also affect our amounts. There is a second step here. We want to look for our net ionic equation. For the net ionic equation, we want to look for things that show up more than once on the left and the right. Nitrate is here in the beginning, nitrate is here at the end. It's floating around, but it does not actually do anything. This is a spectator. Likewise, lithium is here floating around, lithium is here floating around. It is unchanged, does not participate. This is another spectator. Alternatively, lead starts off as aqueous, but becomes part of this solid. This is forming a chemical bond. This is actually participating in that chemical reaction. Same thing with our chlorides. They are forming that solid. They're forming that new chemical bond. This means that those did participate. We can rewrite this with only those highlighted in green. And here we have our final net ionic reaction. Each of these is good for their own purpose. The molecular equation is nice to show what's going on. The complete ionic equation is more writing, but it gives us better intuition about what is actually floating around. And the final net ionic equation is a nice simplified picture that still gives us that intuition. There we go. Now we can rewrite our reactions as molecular reactions, ionic reactions, net ionic reactions. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.